now. So this way we have recording of the class. Has anyone even gotten back to rewatch the video, or was that kind of not really necessary?
It's
Okay.
on my agenda to do the next couple days.
Oh, okay. All right. Okay. So it might be handy. I mean, it doesn't cost me anything to do it. So there's no reason for me not to do it. Just, you know, just because, hey, it might be useful to someone at some point, so there's no reason for me not to do it. All right. So we are getting back to the technical definition or the technical discussion of enclave, TCB, and SRBs. And I was just using that example to illustrate, this bookmark here, where I left off, from last time. That's kind of what a TCB or SRB is doing. It's basically really just a bookmark that says, okay, this is where we left off. Now, technically speaking, it bookmarks what we need to do next, okay? Not what we have just done, but we are, what we're supposed to do when we get back. So technically, it's off by a little bit, but it's really kind of the same thing as, what this bookmark is trying to do here. It's really just marking what we did last time and what we're about to do this time. So I just added a sentence here, so I kept changing things. Let me see. Um, I added something, but not here. Probably added. I added it over here. So when we get to that point, I'll talk about it. All right. So back to TCBs and SRBs, and also the enclave concept. So an enclave is basically representing tasks that are spread across multiple address spaces, and collectively they perform a single action that is that is of value to the application, or whatever the computer is supposed to do that provides value to the client. And in IBM's term, it is called a transaction. So I can leave the bookmark here. There's no need for me to delete it. Just this way we kind of know, how we progressed, through the material. So that's fine. That's fine. So now we have section 2.4. 2.4 explains a very common word, okay, work. Even though the word itself is very common, in IBM documentation, it has a really kind of specific meaning. So I'm gonna just kind of go through the paragraphs one by one. A processor is not work. A processor is the active component that performs the work, but the processor itself is not work. The address space is not work either. An address space specifies how work is supposed to be done, so it specifies the instructions, but by itself, an address space is not work. The execution of instructions in an address space by the processor, now that is work. So from this perspective, so this is what I added just today. Okay, this sentence here is what I just added today. From this perspective, a TCB or SRB specifies where to find the next step of work to be done. So that's kind of how we want to look at the word work in the context of the rest of this module. And also in most of the IBM documentation, this is how we can look at work. So do we have any questions about section 2.4?
To clarify, a service request block
Mm-hmm.
is the primary and a task is within the service request block.
It's the other way around. A TCB, a task control block, is the primary, and
Okay.
then an SRB is you can look at the SRB as a subcomponent of a TCB. So an SRB is needed when we need to perform some work that is not in the same address space.
Okay.
All right.
Mm-hmm.
You can, if you try to relate it to CISP 300 concepts, it's kind of like, when we need to use a subroutine or function, depending on how it is called in that class. And SRB help us keep track of, the execution point of the subroutine. But it is a very kind of special subroutine because it's a subroutine that is not in the same address space as where the request is coming from.
Okay.
All right. So now we talk about the terms subsystems. In a Z system as delivered has ZOS installed and many other subsystems also installed. So the term subsystem is really kind of fuzzy in IBM's documentation. A subsystem is definitely a software component. It is not a hardware component. And also, a subsystem also requires the operating system to be installed first. In other words, I can tell you what is not a subsystem. The hypervisor, a type 1 hypervisor, is definitely not a subsystem because a type 1 hypervisor runs on the bare metal hardware, so it doesn't even need the operating system. That's why it's a type 1 and not a type 2. So that is definitely not a subsystem. The operating system itself is also not a subsystem because it is usually just called the system, okay, or the supervisor. So a subsystem is a software component that need these services offered by ZOS. And then in return, a subsystem would also offer its own services with client-specific apps, jobs, and end users. So in the context, I think you guys already know what is ISPF. So ISPF is a subsystem because in order for ISPF to function, it needs the operating system to be working first. But it also provides its own service, which in this case is a interaction. Well, it's a terminal type of interaction with an end user, but that's why it is a subsystem. DB2 is a subsystem because DB2 cannot function without ZOS installed first because it needs services provided by the operating system. In this particular case, DB2 requires the support of vSAM. So as a result, without the operating system installed, DB2 cannot function. CISC is the same way; it is a subsystem. JES is a subsystem. So all of those are basically components that can function, that can be installed and function once ZOS is up and running.
Is RACF a subsystem?
Which one?
RACF.
How do you spell it?
RACF.
RACF. Okay, we
I
can look
think
it up.
that's the security component, isn't it? That for access.
Yeah, but
Okay.
wouldn't that be considered a subsystem?
It's a
I don't know.
facility. I can take a look here. I would call it is a subsystem too, because it provides services. The services it's providing is authentication, and that in return can be required by jobs and other apps. So I would say it can be considered a subsystem. All right. In general, with IBM, whenever they call something a facility, most of the time it can be seen as a subsystem, but that rule is not always true. So now we want to talk about this next sentence. Not every subsystem is an IBM product. That's basically what this sentence is trying to say. Because Oracle, which you can also install in ZOS, is a subsystem, but it is not from IBM. Oracle is from Oracle. So that's what the term subsystem is referring to, in the context of IBM. Now, what is also interesting about a subsystem is most of the time it doesn't do anything by itself. It's just sitting. It's loaded. It is running in memory. Well, I shouldn't say running, but it is in memory. It has its own address space. It has its own TCP, but it's not actually actively doing anything. most of the time. So instead, what it's doing is it's waiting for requests to come in. So let's use the example of ISPF. Okay, so you can have ISPF loaded, the system has it has it up and running, and you might even have a terminal program, a 3270 emulator connected to ISPF already. But unless you do something, unless you type something on the keyboard, ISPF doesn't really do anything on its own. Perhaps it updates the clock. Does it have a clock? Because I'm not familiar with the display of ISPF. Does it show a real time? Like what the current time is by itself?
I don't know.
Yeah, I
It
don't
does.
read. Yeah, go ahead.
I, I think it does when you first log in. That's a feature you can turn on. But when you're actually in the panels and stuff, it does not display a time.
Okay. So the reason I asked that is because if it does show the real time, the current time, like keep it up to date every second, then it does have something to do like every second to update the clock display on the screen. But it doesn't even do that. So for the most part, it is really truly passive and just waiting for you to type something on the keyboard. Then it will respond to it. It will just respond to your requests. DB2 is the same way. Now, DB2 does not directly interact with an end user. So what it does interact with are basically jobs or apps that will send what we call SQL queries. SQL stands for I keep forgetting what the S is representing.
Is it SQL language?
Yeah, the abbreviation, or we pronounce it as SQL, which includes the SQL. These three characters together is pronounced SQL. If I remember correctly, the S is standard, but I could be wrong. Standard query language. That's what SQL is representing. But I hate to be wrong later on, so I'm gonna look it up.
I'm trying to find my glossary.
Yeah, I can just look up, and it is structured. Okay, I knew I was wrong because I kept thinking it is standard, but it's actually structured. Okay, so it's structured query language. I'm not sure whether you guys need to learn SQL or not, but it is its own class. Okay, this is easily a 3-unit class on its own. But SQL is just a language. Okay, so a lot of apps, especially when we talk about web apps, a lot of the web apps would interact with a what we call a relational database, which DB2 is, Oracle is, MySQL is, and there are many other type of relational databases. And they all basically use the same language. They talk the same language, which is SQL. So SQL is used to formulate a query. In other words, it formulates a question. Okay, the question can be simple as show me all the rows in a particular table in a database. Okay, so that would be a fairly simple SQL query. So until an app sends a query like that to DB2, DB2 as a subsystem is loaded. It is using up memory. Okay, it has its own address space. It has a TCB, at least a TCB allocated to it. Possibly it has SRBs, but that depends on whether it needs somebody else to help it to do what it needs to do. But it won't be using any execution cycle. It won't be using the processor at all until there's a request coming in. So a request that triggers the system to perform work is, for the rest of this discussion, I will just call that a work request. All right. So do we have any questions about the terms introduced at this point?
Not at this time.
All
You
right.
explained them well.
Okay, very good. So section 2.6 is pretty short. All it does is to explain what is a subsystem transaction type. And it starts with explaining because interactions with a subsystem is a request, then you perform the work, and then you respond kind of sequence. So they're also called transactions. So IBM used the word or the term transaction to refer to these three items in a sequence. Okay, so first of all, the client would send a request, and then the server will perform the work, and then after the work is done, then the server typically will respond to the client and say, okay, work is done. Or in the case of a query, it would basically say, this is the answer to the question that you asked earlier. IBM associates each of its subsystems with a type of transaction. The transaction type of each subsystem is important because that determines how workload management applies to that subsystem. So you can see there's a little footnote notation here, a little 2. So if you follow that link, it will bring you to a table where it will describe for each IBM subsystem what type of transaction it would classify as. Now there are two main type of transactions. I can get there in just a little bit, but I can remember exactly what those two main types are. One type is an address space, and the other one is an enclave. So in the case of a address space transaction, you can sort of look at it as a very simple enclave where there's only one TCB involved. In other words, there's only one single point of execution with those transactions. You can also look at an enclave as just a more complex version where it involves multiple address spaces. It involves at least one TCB and any number of SRBs. So that really it's just a matter of complexity. One is very simple, one single address space, one single TCB. The other one is more complex because in order to perform the action that we need, it requires basically instructions that are spread across multiple address spaces. And when you have the instructions spread across multiple address spaces, to track which instruction we're supposed to execute next for each address space, that's why we need the SRBs. Okay, the SRBs help us keep track of the execution point in multiple address spaces instead of TCB, which can only work within one single address space. So that's what section 2.6 is about. And after that, I wrote section 2.6, I found out that for the most part it is not important to know what kind of transaction type is important. It's because both address space and also enclave type of transaction type, they can support all of the Go specification. So there's no problem within those two. It's only when we get to IMS that certain type of Go specification does not apply. So you can only specify, I think, one of them, but not the all three of them. So are we good so far up to this point?
So if I'm understanding correctly, a single address space only deals with a TCB, but an enclave has both TCBs and SRBs.
Right, exactly.
Okay.
Yep. Because even with a single address space, you still need to keep track of, okay, where's the next instruction? And the TCB, is needed in order to do that. In the IBM documentation, they don't specify that. They just say, okay, this is a single address space transaction, and those are enclave type of transactions. But you can basically look at a single address space transaction as one that only needs a TCB, but it has no need for SRBs because there's only one address space involved. Very good. Yep, that's exactly what that means. All right. So now we are moving on to the actual meat, the actual core content of workload management. Everything before this is really just so that we understand the terms and the background information related to workload management. So at this point, we get started with with the stuff that is directly related to workload management. So in this case, a performance goal is a specification that is either met or not. So it's a kind of Boolean or binary kind of thing. Okay, so either we meet a goal or we do not meet a goal. WLM workload manager or management has three types of goals. Now, I would just make it two, but the IBM documentation considered the third one also a kind of goal, so I'm going to have to include it here as one of the types of goals. And by the time we get to that one, you'll go like, okay, that's sort of you'll understand why I call the third one is like maybe we shouldn't call that a goal. Okay. So these performance goal options, basically they are ways to specify performance goals, do not directly relate to whether a job is finished or can finish on time or not. Okay. So this is really important because what we are doing is we are just trying to specify um, a certain aspect of performance, but we cannot specify that a particular job needs to be done in 3 minutes and have the system to guarantee the completion time to be in 3 minutes. There's no way to specify that. The reason why it's impossible to specify that is because it's really difficult to analyze an algorithm. Okay, an algorithm is basically just a way to specify how something is done, and that's what you learned in CISP300. So it's really difficult to mechanically analyze an algorithm, and even if we know how long each step may take, but because of the concepts of conditional statements, okay, sometimes we can go this route and other times we go the other route, and also because of the concept of looping, basically we're doing something in a repetitive fashion. But those concepts are difficult for a compiler or any type of computer tool to analyze to the point where it can tell you exactly how much time it is going to take to complete a particular algorithm. So that is not what performance goals are about. In order to roughly determine the actual total duration of a job and whether it can be done, a programmer or software engineer or computer scientist must evaluate the time complexity of all the parts of a job and combine the time complexity analysis with work request performance goal option to get a rough idea of whether a job can be done on time, given that somebody said, okay, I want this to be done before 5 a.m. Okay, so it takes a lot of expertise, okay, because the reason why I put all of these people here, programmer, software developer / computer scientist, because it all depends on the complexity of the job involved. If the job is fairly straightforward, like it is a sequence, okay, we do this and then we do this and then we do this and then we're done, then a programmer, can probably, estimate, how much real time it's going to take, as long as we know the response time for all of the work requests. If it is a little bit more complex, it involves some kind of looping, nested conditional statements, and stuff like that, then we might need a software engineer to roughly estimate how much real time it's going to take to finish a job. If the algorithm involved is really complex, okay, then we need a computer scientist to do it, because at that point it becomes more or less a math problem. And computer scientists are the one who would analyze algorithms and come up with what we call the time complexity of algorithms. So did you guys get some exposure to time complexity when you took CISP 300, or was that concept not mentioned?
Was not mentioned.
It was not mentioned. Okay, that's fine. It's not a problem. So I can explain it very, very briefly, just so that you have some idea of what this word time complexity means. So time complexity is basically looking at the trend of how much time it takes for an algorithm to finish in relation to the size of the problem. So there are certain types of algorithms where the amount of time it takes is the square of the size of the problem. So if you double the size of the problem, it will take 4x, it will take 4x the amount of time to finish the job. If you triple the size of the problem, it will take 9 times amount of the time. So those are not very nice algorithms because it is what we call superlinear. And then you have the usual linear complexity. So linear complexity means if you double the size of the problem, it will take twice as long. If you triple the size of the problem, it will take 3 times as long. So those are called linear time complexity. And then there are algorithmic time complexity, where you can double the size of the problem and it only increases the amount of time by just a little bit. Okay, so those are the kind of the rare type of algorithm, but there are such algorithms where you can double the size of the problem and it just adds a little bit to how much time it takes to finish the job. So when you see the term time complexity, it's really just talking about the curve that relates to the amount of time it takes to finish a job versus usually the size of the problem. So when I talk about the size of the problem, you can kind of think of that as the number of records to process. Okay, in the case of I guess franchise tax board. Okay, if you have a job to run, it is basically time the size of the problem is basically asking how many returns are we processing, how many corporations are we processing, and so on. So it's basically just a number of items that we need to process. That is the size of the problem. So I'm not going to spend any more time to talk about time complexity, and instead we'll get into the 3 ways they can specify a performance goal in WLM, in workload management. The first one is called response time. So in this case, in the case of a subsystem typically associated with interactive user requests, such as the TSO subsystem or ISPF, or something that is interactive, that has to do with interactive requests that originate from the web, then an important goal to specify is response time. So when you're using ISPF, okay, and you type something on the keyboard using the terminal emulator, then the question is, well, how soon would a normal end user expect the screen to update? When you type something and then press the enter key, now that time is kind of soft. Okay, this is what we also call a soft real-time type of problem, because, well, if it's a quarter of a second, it's definitely good, because most people do not mind if they have to wait 1/4 of a second before the screen would update. Not a problem. Half a second is noticeable. Okay, if you press the enter key, it takes about half a second for the screen to start to update. It is noticeable, but probably won't bother a whole lot of people. But if it takes 10 seconds, then we have a problem. Okay, so that's the response time. Okay, when you press an option and then the enter key, what is the amount of time between the last keystroke that you press on the keyboard and the screen starting to update, showing you that, okay, I got you, I'm updating the screen right now. The other one are the live interactive requests originating from the web, because so requests coming from the web, usually we refer to those as HTTP requests. So HTTP stands for Hypertext Transport Protocol. It's not important to understand the protocol itself, but what is important is when you send something. Okay, I'm just going to go to Wikipedia. Okay, so I go to Wikipedia on a particular page. When I click on a particular link like this one, that is an HTTP request to the Wikipedia server. So now the question is, when I press a link, okay, to get to another web page, how long does it take for the screen to update? That is the response time that is important, because a lot of times the HTTP request is triggered by an actual person, an end user clicking a link. Not always, okay, because we have web type APIs where a server can talk to another server using HTTP. So in those cases, there's no actual end user involved. So, if it has to wait like 5 seconds, probably it's not going to be a big deal. But on the other hand, if you're dealing with something like this, when an end user is clicking on a link, then taking 5 seconds to update is kind of long. I mean, that really is not a very good end user experience. So some of you might be saying, what kind of website would take more than a second or two to update or to get to a link? I will show you. I will show you with what website would do that. So I'm going to type in CCCCO Mesa because I just did this test a little bit earlier today. So this is the math, engineering, science achievement portion of the CCCCO, which is the State Chancellor's Office. So I click on this link. I'm still waiting. It's still waiting. So this may not be acceptable, okay? Especially when you're dealing with corporations, because IBM serves a lot of huge organizations. The California state government is one, but it also serves Wells Fargo Bank. It also serves American Express. So with those corporate customers, when the website takes this long to update, to come back with a response, that is not okay. That is not okay because these corporations will start to lose customers to competition. So this is
I would
what
have already clicked off. I would have been done.
and it was still being loaded. I mean, it never finished loading. And I know it is the right link also because otherwise it would have told me, oh, 404, right? Not found. So that's the kind of response time that we are talking about. So this is why response time is one performance goal that you can specify for work to be done. Okay, so the next question now is, how do we specify a performance goal in terms of response time? So the way it is specified, there are two ways to do it. One way is to do it like this, where it is represented by a percentile and a threshold. So in this case, we have a percentile of 90% and an actual threshold of 250 milliseconds, which is 1/4 of a second. So what this is saying is, to meet the performance goal, 90% of the work requests must be done within 1/4 of a second. That's how one way you can specify a response time performance goal. But now the question is, what about the other 10%? Because if the goal, if we are meeting the goal by saying 90% of the time, it is within 1/4 of a second, that meets the goal, then what about the other 10%? It doesn't say anything about the other 10%. Okay, so the other 10% can be very, very bad, like 10 seconds to update something. So that's one way to do it. The other way to specify a response time goal is the average. So you're basically just saying, on the average, we want the response time to be 250 milliseconds. So you can do it one way or the other. Okay, and that's for response time. And response time, once again, is really important when we are trying to specify work done that has to do with end user triggered action, because you don't want the end user to just kind of walk away and go like, this is not working, I'm just going to walk away. All right. So are there any questions about the performance goal of response time?
Did the website ever load?
I actually I closed the tab already.
Okay.
Yeah, and it's not just today either. I have tried to access different types of documents from the State Chancellor's Office, from their website, the CCCCO website, and every single time, most of the time it is like this. And apparently, nobody complained or nobody paid attention to the complaints. So that's just interesting to me. So that was a good question. Thank you.
I always think that if I click on a link and it's not working, it's just circling. I always think that it's just a fake link. So I get out of it.
Yeah, I mean but in many cases, but the CCCCO is not is a very important organization because that's the okay, CCCCO and Converse Zoom actually are very related. So CCCCO stands for California Community College Chancellor Office. That's why we have four C's. And the Chancellor's Office is also what set up the Converse Zoom, arrangement with Zoom. Um, so a lot of the instructions to use Converse Zoom, may link to a document in at CCCCO's website. And you can probably imagine the kind of frustration when people say, "Okay, I want to be able to sign into, Converse Zoom, and or I want to use a particular feature of, Converse Zoom." They go to a particular link, they click on the link, and the page never loads, or it won't load in 10 seconds or 20 seconds. Yeah, so that's kind of interesting. That is really interesting. And I know at least one of you works for CDT.
Three of us
Three of us.
do.
Okay, so with the CDT, it's an interesting issue because the CDT is not specifying the actual application. It's providing a service, for other state agencies to utilize it. That's my understanding. Is that correct?
Yes.
Okay, so if there's a configuration issue or if there's any type of issue that causes a response time, the end user experience response time, who is going to be who would be in touch? Who would be contacted in those cases? I'm just curious.
They would have to fill out like a incident report, and then it gets routed to the service desk, and then the service desk determines what area is responsible for whatever the incident is, and then
Okay.
it gets forwarded to that unit for resolution.
Okay, so would that unit be a part of CDT or would it be part of the client of the CDT?
It'd be CDT
It'll be
internal
okay.
first, and then we would determine whether it was on our end or the client's end
I see.
or something to do with the mainframe itself. So
I see. That makes sense. Okay, it makes sense that the incident is reported to CDT first, so that the CDT staff can look at the incident and try to differentiate: is it our stuff that's causing this, or it's the code that our client wrote that is causing this issue to happen. Okay, that makes sense. Okay, all right. Thank you. All right, that's section 3.1. So now we can work on section 3.2, which looks simple, and it really is not too complicated. IBM does have a fairly convoluted way, okay, and I kind of whisper convoluted way to specify velocity. So let's take a look at velocity. Velocity is a ratio, so it's basically a number divided by another number. So it's a ratio of how often requested work gets to use the processor or system input-output devices. All right, so and this is specified as a percentage. And if you want to specify velocity as a performance goal, this percentage can range from 1 to 99. It can never be 100%. You can get up to 99. All right, so the question now is, what exactly is the ratio of how often requested work get to use the processor or system devices? In other words, it is actually using the mainframe, hardware. It's not waiting for something, it's not sitting on the sideline, it's actually doing work. Okay, that's basically the ratio. So now the question is, how do we know? So as it turns out, velocity is usually determined by sampling. Okay, so when I say sampling, I mean while a particular requested work is in progress, okay, what the operating system is going to do is to basically ping it, once in a while. So it would just ping it and go like, are you actually doing work right now? And then after X many milliseconds, it's going to do it again. It will basically go to that specific task and say, are you actually doing work, or are you waiting for something? Because it is entirely possible that it has to wait for something. So by doing this kind of sampling and basically separating the category of yes, you're actually doing some work, or no, you're waiting for some resources and therefore you're just idling because you cannot get work done. So by looking at those numbers, we can figure out, how often as a percentage that particular task is actually doing work. And that ratio, okay, the ratio of doing work versus all the samples, okay, let me rephrase that. So the number of samples where we can confirm the task is actually doing something versus the total number of samples that we have performed, that ratio is what we are trying to specify here as a performance goal. All right? Is that okay, or do you guys have any questions about what velocity is actually measuring?
So it only fails when it's pinged and it's waiting for its turn to do work? Or what if there's no request for it to do work at all?
So when there's no request, there's no velocity to measure. So the sampling only occurs when the subsystem has already said, okay, I got it. Okay, you want me to do blah. Okay, so as soon as the subsystem acknowledges that it is handling a work request, that is when we start the counting of the samples. Does that make sense? So when the subsystem, like when DB2 is just idling because nobody asked it to do anything, we are not collecting samples because that would not be. I mean, that's because the samples that we collect in those cases is not going to be helpful. So we only start to do the sampling when DB2 accepts a request from a client. In this case, a client is basically just a job. Okay, so as soon as DB2 says, okay, I'm taking this job, then we start the sampling, and we keep the sampling. We keep doing the sampling periodically until DB2 says, okay, I'm done with this job. Then we stop the sampling. Is that okay, Lupe?
Yeah, that's fine.
Okay. I'm trying to think of an analogy so that we can. Okay, think about a fast food place. Okay, so think about a fast food place where we want to see the utilization, okay, of employees. Okay, so what we do is we have a video camera or body cam on each employee. Okay, and we don't really do any type of monitoring until an employee has a job to do. So in other words, if the fast food place has no customers, okay, nobody came in, nobody is at the drive-through window, waiting for orders, and nobody's actually having any actual work to do, then we don't care. Okay, we are not doing any sampling. But as soon as a customer walks in and places an order, then we start the sampling. So the sampling is really just looking through the recorded video and just count the number of frames where the employee is actively doing something versus waiting for something to happen. Okay, so what can we possibly be waiting for? So in the case of a fast food place, it is possible that the employee says, okay, we have just used up the last of all the fries, so now it's time to make a new batch, and the employee is just looking at the fryer, waiting for the fries to be done. So that would be not actually doing work, because what is actually doing work is the employee taking the fries container, putting it into the little container thing that we hand over to the customer. That is work. Or the employee is wrapping up a hamburger. Okay, that is work. Or the employee is making change, to return to the customer. That is work. But if the employee is waiting for something to happen, in order to continue the work, for whatever reason, that is not work. Okay, I can give you another example. So let's just say that there's only one soda fountain, in this particular fast food place, and a lot of orders are coming in. Some coming from the drive-through, and some are coming in through the walk-in, customers. And because there's only one soda fountain, all of these orders eventually will have a bottleneck at the soda fountain. So let's just say that we have 5 employees, but only one can be using the soda fountain at a time. So the other 4 are just waiting in line, waiting for the first one to be done. So in that case, basically all 5 employees would not be actually doing work. Okay, they will not be considered doing work because they're all waiting for that 1 cup of soda to be filled. Is that okay?
I think so.
Okay, very good. So in this case, velocity is specified in 1 to 99%. So this is basically a target velocity. So velocity is tricky because it is very it's relative to everything else. Okay, so when we use velocity to try to specify performance goal, we really have to kind of think about what else the system is supposed to be doing, and the job that we want it to do, how important is the job. So there's a lot of black art going in, determining the velocity specification when we want to specify goal performance. So now we get to the third one, the one that I said I am not sure this is a performance goal because it is called discretionary. What that means, okay, it explains down here. What it means is work request can only use the excess resources. In other words, when there's absolutely nothing else to do, then we can perform this particular work request. That's what we mean by discretionary. So there are only really 2. Okay, as far as I'm concerned, there are only 2 goal specifications, which is by response time and also by velocity. Because the third one basically just says, well, if you have time left, if you have resources left, let's do these things. Okay, but otherwise, they don't, we don't have any specific goal to achieve, with those particular work requests. All right, so I'm gonna pause and see if you guys have any questions at this point. No questions?
Not
Hold
I.
on, I got one.
Okay, go
so
ahead.
they can only have one of these 3 performance goals at a time.
Yes, so a work request, okay, or the work corresponding to a request can only have one of these 3 specifications. So you cannot specify 2 both at the same time. You cannot have response time and velocity specified at the same time. That's my understanding. Okay, there's. I tried to look this up and I could not find a specification from IBM's own documentation. But I can tell you, it doesn't make sense to have discretionary and one of the other 2 specified at the same time because that would be contradictory. Because when one says, okay, we'll use the excess resources, it doesn't make sense to specify response time or velocity at the same time because that's just contradictory. So it is my understanding, which can be incorrect, that you can only specify one of these 3 when you want to specify a performance goal. All right. Any other questions? right. So the answer to answer the question, Lupe's question, one way to answer that question is to look into actual screenshots of the WLM, because by the time we get to the portion, they call this surface class. Okay, these are all specified when we specify surface class. So in the surface class screen, okay, if it gives you an option of what kind of performance goal you want to use to specify, that means that implies that you can only specify one of the three. On the other hand, if it gives you the fields, okay, and they're all empty, and you can specify more than one at a time, especially the first and the second one, then I would be wrong to say that you can only have one of the three. So I can look into that and come back with an answer. Let me put a bookmark here. Alright, so I am going to look this up and hopefully come back with an answer in the next class. Any other questions? Alright, if there are no questions, we're going to move on. So the next topic has to do with surface importance. So suddenly we introduced this new word of surface. So surface is basically work requested. So what we refer to as work requested is now called surface. So there's an importance level that you can associate with all the surfaces. In fact, you have to specify an importance level whenever you want to use the WLM to specify what we call a surface class, which we'll talk about next. And the importance can only be an integer from 1 to 5. So don't ask me why it is only from 1 to 5 and not 1 to 10 or 1 to 8, okay, or 0 to 7. That's how it is set up, okay? So it can go from the most important, which is importance level 1, all the way to the least important, which is importance level 5. Now, when you specify a surface class, okay, which is it's a part of a surface class specification, and if you don't specify anything, it will default to a value of 3. So 3 is kind of like average. 2 is slightly important, 1 is highly important, 4 is not too important, and 5 is not important at all. Okay. So what does it mean? Okay, what does it mean when we have surfaces that are of different importance level? So what that means is when we try to meet the performance goals, we'll prioritize. Okay, the system will prioritize to first make sure that the performance goals of everything of importance 1 to be met first. And only when that is satisfied that we move on to surfaces of importance level 2. And only when the jobs or the surfaces that has importance level 1 and 2 done, have those performance goals met, then we'll try to allocate resources to surfaces of importance level 3 and so on. Okay, so this is a really important number to associate with the surfaces, because it basically says if you have importance level 4, even if you specify a very high velocity or a very quick response time, it's probably not going to be met unless all of the other importance levels are done already. Have all the performance goals of all the more important surfaces are met. Okay, so that's why the importance level is a very important number, and it's probably not something that a system administrator is going to determine, because this really depends on the services being offered, how important is that to the organization itself? So it is probably a joint decision between the management people who will basically set priority and go like, okay, so if something has to go, these are the things that are optional, but these things are so important that we cannot not meet the performance goals. So those are administration decisions to make, and the system administrator most likely are just going to be making sure that the correct level of importance are entered into the system. So are there any questions about the importance level of a service?
Is that going to be tied to like the service level agreements that we have with the customers as to the level of the priority of their work?
Yes, I would say there's a very strong correlation between your SLA and the importance of the work requested, related to the services. Um, but there's probably not a one-to-one correspondence because in SLA, okay, so you guys can educate me. When we talk about an SLA, a surface level agreement, what does it entail? What does it specify?
Well, my understanding is that the service level agreement is how the customer gets charged and how in regards to how important their jobs are and the priority of their jobs versus other SLAs.
Hmm.
So the higher the importance,
Mm-hmm.
then it's written in their SLAs
Hmm.
or certain agencies, I guess I would say. I'm not sure 100% on that, but I
I
think
believe
it's
it.
a
Sorry.
go ahead, Lupe.
I believe it also has to determine with uptime as well,
Mm-hmm.
when systems available to them.
So it's not just the importance, right? SLA is a much larger document that has more, I would say, parameters, to what is considered meeting the agreement and what is considered not meeting the agreement. I can try to look it up, just kind of real quick. Um, so we can look up SLA California State. Okay, surface level agreement, right?
I think it's service.
Hmm?
I think it's service.
Just surface.
Yeah, like service level agreement.
Oh, okay. Well, brings us right to CDT's website. Hopefully, this loads like quicker. Yeah, I was thinking if this loads, like the CCCCO website, we have a problem. Okay. All right. So, hosted service level agreement (SLA) provides standard roles, responsibility, and expectations. So it's the expectations part that we are more concerned about because we're talking about workload management. Um, I'm just browsing through really quickly. All right, so these are the priority level, but they talk about incident priority level. So they do not they don't correspond to response time or velocity in this case. Because when you have something that has a low velocity or low importance, it doesn't mean it doesn't get done. It simply means it gets done in time. there's not a whole lot of guarantee of when it is going to be done. All right, so this might need a little bit more digging. Yeah,
So
this. Yeah, go ahead.
on Wikipedia, it breaks it down into like 6 different types or 6 different components. Um, the services to be provided, the service's desired performance level, especially its reliability and responsiveness,
Mm-hmm.
monitoring process and service level reporting,
Mm-hmm.
the steps for reporting issues with the service, response and issue resolution timeframe, and then repercussions for a service provider not meeting the commitment.
So I think it's the second item that relates to WLM. So now the question is, how do they specify, what level of performance the system is supposed to provide? So I think in that case, they will still be using response time, especially on the website. It will still be based on the response time. But when you have a job that is a batch job, then it is a question of can it be done before a certain time? Because if I would think that's kind of how it will be specified. For things that are in a batch job setting. Okay, so getting back to here, we can understand how response time relates to things that are interactive, okay, especially when there are end users involved. So that makes sense. Velocity, on the other hand, it makes more sense when it comes to things that are in batch mode. So let's just say that we want to print out paychecks, okay, for the entire state of California. That doesn't really talk. It's not important to talk about response time in that case. It makes more sense to talk about velocity. Okay, of all of the samples of whether DB2 is doing work for a particular job, we want to guarantee that 90% of the time we want to make sure that we get the resources that we need so that we're actually doing work. So it makes more sense to use velocity. Velocity combined with importance is, I think, ultimately what is going to determine the actual performance of a batch job. But there's no, I'm trying to think of the word here, but there's no mathematical way to look at just the velocity setting and also the importance, because it also depends on what other things the server is doing, because everything is basically relative to everything else. So I think it's going to be it's a tough job, I think, to determine importance and velocity in the setting of a WLM by just reading the surface level agreement between CDT and their clients, because now it's a question of how do we balance these things, right? Does that make sense?
Paychecks should always be a 1.
Say that one more time.
Paychecks should always be a 1.
Page X.
Should always be 1.
Paycheck.
Highest priority.
Oh.
It's a joke.
Oh, okay.
Because we're the ones getting paid.
Oh, paychecks. Okay. I didn't quite get the word. Yep. Okay. All right. So after all of these things, all the way up to section 4, now we have the vocabulary to specify, a surface class. So a surface class is basically the packaging of related attributes. So there's the name of the surface class, and a few other things like description, but we want to focus on more of the important stuff in a surface class specification. So a surface class specification would specify performance goal, and we already talked about the 3 types of performance goal we can specify. So we have response time, which can be in percentile and a threshold, or it can be specified in an average. We have velocity, and then we also have discretionary, which basically just says, when there's excess resources, this type of work can be done. And then the second attribute is importance, which can go from 1, which is the most important, to 5, which is the least important. But the surface class has also some additional stuff, okay? And some of this is actually um, it's not very directly specified when you read IBM documentation. So one of these is the concept of a period. So most people think about the term period and they just go like, okay, so does that mean, when a particular surface class is in effect, like a certain time of the day or certain days of a week and so on? The answer is actually no. Okay, a surface class period is basically a component of a surface class, and you can specify up to 8 surface class periods per surface class. So you can basically now think about, okay, here's a surface class, it is a folder, and then inside a surface class folder you can have up to 8 surface class periods. Okay, so now what exactly is a surface class period? So a surface class period would share the same, all the surface class periods would share the same name and the same description. However, each surface class period has its own performance goal and has its own importance specified. All right, so now the question is, then which one are we supposed to use, right? Because there can be up to 8 of them. There's at least one, but you can have up to 8 surface class periods corresponding to the same surface class. So the way it is arranged is we always start with surface class period 1 when we want to determine the performance goal and also the importance. Then the next question is, well, then how do we move from surface class period 1 to surface class period 2 and so on? The answer to that question is when we use up all the resources specified by surface class period 1. That is why it's called a period, because in the period it would specify how much resources, total resources, we are supposed to use up for a particular period. So what I have highlighted here is called a duration, and the duration is not a real-time duration. In other words, it is not in number of seconds, minutes, hours, days, weeks, and so on. A duration is specified in what we called, what IBM just calls surface units. Okay, that describes a whole lot, right? So what exactly is a surface period, a surface unit? So a surface unit is computed by this particular average, I wouldn't say average, but it's a weighted sum of specific terms. So when you look at each term, it says your CPU times CPU surface units, SRB times SRB surface units, IOC times IO input output surface units, and then MSO times storage surface units. These terms, okay, just CPU, SRB, IOC, and MSO, those are coefficients. So when I use the term coefficients, it simply means it is just a value. What kind of value are we talking about? It can be 0.5 for CPU, 0.2 for SRB, 0.2 for IOC, and then 0.1 for MSO. It can also easily, just as easily, be 10 for CPU, 5 for SRB, 2 for IOC, and let's say 8 for MSO. So there's no real restriction of what kind of coefficient we can use for CPU, SRB, IOC, and MSO. The actual surface units, those are measured in time. Okay, so those are actual seconds. So we are measuring, how many actual seconds that the processor, the central processing unit, is actually doing work for a particular surface. Okay, so let me put this in perspective. In a particular analogy. Let's think about a vehicle. So let's not think about data processing. Instead, we are thinking about delivering packages. Okay, So we think about UPS, think about FedEx, think about Amazon and the USPS. Okay, so what a duration is trying to measure in the context of UPS is the total cost of running a truck. That's basically what it's trying to measure. So, what kind of things would contribute to the cost of running a truck? So, instead of CPU surface units, we might have the total number of revolutions of the engine. Okay, because the more you turn the engine, the axle in the engine, the more likely it's going to break down. Okay, so that's one thing we can measure. The second one, can be measuring the actual distance traveled by the truck. Okay, because how many times the engine has turned does not always correspond to how far the truck has moved. Because it's possible that the truck is just idling a lot, so it's basically turning a lot in the engine, but it's not moving a whole lot. But it can also easily be the other way around. The truck is on the highway a lot of times, so it's actually going a lot of distances where you would have tire wear and other things that happen when you're actually moving. Okay, the accident rate is going to be higher when the truck is moving compared to it's just idling somewhere. This can correspond to the wages of the person who's driving the truck, right? And let's say this one can be corresponding to I'm trying to think of another measurement of the cost of running a delivery truck.
Wouldn't that be the amount of packages it could hold, or
Not quite that, because that's what we wanted to do. It's not the expense of running the delivery truck. So we have engine wear, we have tire wear, we have the salary of the person. We'll just say insurance. Okay, so this has to do with the insurance, of running that truck. Okay, because that also depends a lot on what area are we running the truck, and the age of the truck driver and so on and so forth. Okay, so these are actual number of revolutions. This would be measured in miles. This would be measured in, what was that again? Oh, right, wages. So this would be measured in dollars. And this one is also going to be measured in dollars because it is the insurance, okay, the premium of insurance. Okay, but what about these coefficients? The coefficients is up to the person who wants to come up with the surface units to determine. So in some cases, okay, we can put a heavy weight on the engine revolution. In other words, if the truck is just idling, because the engine is not very reliable, that's going to be important. Okay, we want to put more weight to just how long the engine is running. Okay, in some other cases, let's just say that the trucks use very expensive tires. Then we want to put more weight over here because that's going to be contributing a lot more to the cost of running the truck. If the truck is being run at in an area where there's a lot of accidents or thefts and whatnot, then the insurance is going to be the key factor. So we might want to put more weight into the insurance. So that is basically what we are dealing with here. A surface unit has no particular unit by itself. It really is just a weighted average or weighted sum of all the subcomponents of all the things, all the resources that we need for a computer to work. Okay, so in this case we have CPU time, we have surface unit time, we have input output resources, and then we have how much storage we are using, what is the capacity that we are using. So all of these things added up would be the surface unit. In other words, we just specify, okay, when we specify a surface class period, we specify a total amount of surface units. And when that amount of surface units are consumed, then we move on to the next surface class period. And when that is consumed, then we move on to the next one, and we can have up to 8 surface class periods corresponding to exactly the same surface class. All right, so any questions?
It's a little confused.
I agree.
It is confusing because
Because it says here in the first sentence, it's an integer within the inclusive range of 1 to 8.
Mhm.
And then how do you come up with 1 to 8 when you have all these units that you need to add? I mean,
Oh, okay. So the 1 to 8 is only designating of the potentially 8 surface periods, which one are we defining? So this is an ID. This is an identifier to to the definition of that particular surface class period. We are basically saying, okay, I am now defining surface class period 1.
oh, okay.
So that's what this number is. And you can
Is
have
there
up.
a range? I'm sorry to cut you off, but to determine if it's a 1, is there a range of the total service units that you.
It's up to you to decide.
Oh,
Well, okay, I
okay.
shouldn't say you, but it's up to the system administrator to
Right.
specify the total amount of surface units corresponding to a particular surface class period. Now, the funny part is the last one, the last of the 8 or potentially up to 8 surface class periods should not have a surface unit specification. Because if it does, that means after all of the surface units are used up for the same surface class, the computer would just, or the mainframe would just say, nope, we don't have anything left for this particular surface class. I will not do any more requested work of this kind anymore. That doesn't seem to make a lot of sense, right? So that's why, if and there are certain surface classes that can only have one single surface class period. And if I remember correctly, IMS is one of those. So in those cases, you do not want to specify the surface units here because it doesn't make sense. Because if you specify a surface unit, it is going to be a finite number. It's going to be a specific value, which also means, in the presence of surface units and that amount is actually consumed, then after that point, the workload manager will basically say, we are not going to do any more work of this kind any further. And in almost every single case, that does not make sense.
Okay, so I have one more question.
Yeah, go ahead.
So let's say I need to specify the total service unit.
Hmm.
So this formula, let's say CPU times CPU service units.
Hmm.
So what am I multiplying? I'm sorry.
Okay,
Am I
so there's
multiplying?
another. So there's a particular configuration screen, that will let you specify
Oh,
the
okay.
coefficients. So these things, the CPU coefficient, the SRB coefficient, the IOC,
Oh,
and the MSO coefficients, those are all specified system-wide in a different
okay.
screen. Okay, so once
Oh,
those things are specified, then you basically just specify a single number and say, okay, when these things all add up to this much, then we move on to the next surface class period.
okay.
All right? So this gets really kind of complicated, right? Because you can basically say, okay, for the first surface class period, we'll specify importance level 1, which is the most important, but we only specify a small amount of surface units. So what that's going to do is to specify, the first bunch of work requests of this kind is going to be done really fast because it is of high importance. We're going to put a lot of resources into it. Then you can go to surface class period 2, and then you can change the importance because the surface class periods, each one has its own performance goal and also has its own importance. And they don't have to be the same. They don't have to be in the increasing order. They don't have to be in decreasing order. They are all independent. So, from the perspective of the person who's planning how to use the resources of the mainframe computer, on one hand, this gives that person a lot of flexibility, and at the same time, it also can potentially create a lot of headaches because because now you just have a lot of moving parts. Okay, and remember, every single surface class can have up to 8 surface class periods. So if you have a whole bunch of surface classes to begin with, then it gives you a lot of options of how these different surface classes are going to interact with each other. Who's going to use up your first surface class period one first? We don't know. I mean, it all depends on, in runtime, when you're actually running the jobs and doing all the interaction, you know, how we use up all of these surface units. There's no easy way to predict, especially when the system is responding to something that is interactive. Now, if all the jobs are batch jobs, it's probably easier to plan out things and determine how we want to configure the surface class periods. But when there's a lot of interactive stuff going on, it's not that easy. So, but do we understand what it is? What is a surface class period? Because I know it is a confusing concept because it is a component of a surface class and it is also sequenced. So when you specify up to these 8 surface class periods, it will go from surface class period 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8. And the logic to move on to the next surface class period is that somehow we have consumed all of the surface units that we specify for the duration of that specific surface class period.
So would like a service class period be for like a 24-hour period?
Nope,
and then it would start all over the next day, or?
I do not think so. I think these are starting from the system start time and going forward. Because it's just measuring the total. So they don't get reset, I should say. They just do not get reset until you reboot the system.
Till like an IPL?
Yes. Now, you don't have to specify a surface unit and you don't have to specify more than one surface class periods. It just gives you the option of doing so.
Oh, okay.
Yep.
Well, for example, I work at DMV,
Mhm.
and we're in production, meaning we provide all kinds of reports. There's daily, there's weekly, and monthly, and it's just 24/7. We have a day shift, swing shift, and grave.
Mhm.
So it's an ongoing thing where, well, we do more of the batch processing at night, but all day long, we are just submitting jobs, triggering, and statusing jobs pretty much all day long. So when it comes to workload management, so the workload manager in the COS is configuring all this workload that we submit, right? And would manage which one needs to be done first, right?
It's not only trying to manage what is going to be done first, because they're all really getting done at the same time, or I should say there are multiple things that may be being done at the same time. Okay, and the workload manager is dynamically trying to throttle how much resources to throw at a particular work request based
Okay.
on who is asking whom for what. When we get to surface classification, it will complete the picture a little bit more.
Okay.
But I think I need to correct myself potentially. I need to look this up again because you can change policy. Okay, you can change a surface policy even though there's only one single surface definition. Under that definition, there can be multiple surface policies. But I think when you switch surface policy, it would reset all of these durations from all the way back to 0. So every single surface class would go back to surface class period 1 with no duration, at that time, and it will start accumulating, at that point forward.
Okay.
But I have to look it up, okay? But it just makes sense to me that when you switch policy, that it would reset all of the counters, so everything start from 0 again. So, but I do have to look it up. Yep, this one is kind of interesting. I was actually watching a YouTube video that was just talking about, how what are the pragmatic approaches to make use of the workload manager, and it's really interesting. All right, so so we are not done yet as far as surface classes are concerned. So every surface class, or I should say every single surface class period, can also be associated with a resource group. So a resource group, if you want to think about it, is really just it allows you to specify a minimum and a maximum of your resources that you can throw at a particular surface class. So you can basically define and go like, okay, this type of surface can should get a minimum of 0.1 of all the CPU resources, but at the same time, don't give it any more than 50%. So you can specify a range of how much resources you can throw at a particular surface class period. So that's what a resource group is doing. It just gives you the additional ability to specify a minimum, the lower bound, and also the upper bound of how much resource you can throw at a particular surface. So are we still doing okay so far? Because
I
there are
think so.
okay. Because there are a lot of terms being thrown out here, and a lot of concepts being thrown out too. So now we move on to workload. So workload is an actual technical word in the WLM. And the interesting part is if you look up the definition of a workload, it is very simple. It consists of two things. One is the name, which has to be unique amongst all the workloads that you want to define. The second one is a description, which is just a description for people to read. It's not even for the mainframe computer itself to read. That is a workload. So that means, so how does the name or the ID of a workload, how is it used? That is used when we need to specify a classification rule. Okay, a classification rule, you can have a whole bunch of classification rules, but each one is going to look like this. So every single classification rule is going to specify a very specific instance of who is requesting what work to be done by whom. So that means, on one side we have a way to specify who is requesting the work. Okay, which subsystem is the work request coming out of? And then on the other side, it can a rule can also specify who is supposed to perform the work. So that means you can specify JES as the subsystem that is generating the work, that is originating the work request, and then in a separate rule you can specify that DB2 is the subsystem that is actually doing the work. So this is what I mean when I said, who is requesting the work and who's doing the work. So using this information, a single classification rule can specifies a work qualifier, and it can associate a surface class, which is what we just described, up here, with that particular work qualifier. So a classification rule is basically looking at all the incoming work requests. It try to match up and see if to see which rule fires. Okay, basically a rule has a condition that says that basically specify that it specifies a particular work qualifier, and the work qualifier can specify the client. It can also specify the worker, the server, and it specifies a particular pattern. Okay, it doesn't have to be a pattern. It can be a very specific term that they call a name. We'll talk about that in just a little bit. If the condition is met, then the requested work will connect or be associated with a surface class by name. So every single surface class has its own name, which is an identifier. It's just it just helps us to distinguish one surface class from another surface class. So that way the WLM knows how the work request fit into the overall workload management process. Alright, so we will just kind of make sure that this paragraph is understood before we move on to the details of the work qualifier. So let's see if there are any questions related to the first paragraph here. All right. So if you have any questions, don't hesitate to bring up the question. And I did not keep track of the text channel, but there's no traffic over there, so we're good. All right. So a work qualifier has a type and a name. The type is basically specifying a particular field of a work request. So the field of a work request can be the name of the subsystem, can be the name of the user. Basically when you have a job, the job has a user associated with it. It can be related to the okay, so if you want to know what qualifier, what are the available qualifiers, you can look up the link under footnote number 6. Okay, so there's a long list. Okay, if you follow that link, there's a long list. So the type specifies what we are looking at, and then the name specifies when a match is going to be made. So one specifies where to look, and the other one specifies what we are looking for. So if there's a match, then we basically associate that particular work request with whatever surface class is specified by that rule. So any questions about this?
Is this referring to like a job?
A job is one type of work request. So let's take a look at the footnote number 6, because I think that will help us get an idea of how flexible each rule can be. Nope, that's probably not what I want to do. There we go. There we go. Alright, so the name field for work qualifier is 8 characters long. Well, most things are only 8 characters long in ZOS. So those 8 characters can designate where we're looking, and we can look up accounting information, client accounting information, client IP address, client transaction name, client username, client workstation name, and so on. So we can designate where we are looking, and then the name part of a work qualifier specifies, what pattern, what constitutes a match. So this way, a particular rule can help us. It will basically help us qualify, a work being requested. And this is a huge, gigantic, table. On the columns, we have the subsystems. So we can see CISC as one, DB2 as one, IMS as one, JES as one, and TSO as one. So these are basically the subsystems. And then on the roles, we have, whether a particular attribute is available for a work request coming from that subsystem, or when it is related to that subsystem. So to read this, we can see that, if the subsystem is DB2, we can get accounting information. If it's from DB2, we can get client accounting information. We can get the client IP address, and so on. On the other hand, if it's coming from TSO, then we can get accounting information, but there's no client accounting information, there's no client IP address when it is a TSO, when it's coming from the TSO subsystem. So that is how we can tell which subsystem can use which work qualifier. So it's a pretty big table. I mean, this table goes on and on and on, but all the dots here will help you understand what we can use for a specific subsystem. Is that helping, or is it making it even more confusing?
A little bit more confusing.
Okay. Let me see if I can think of an analogy. Okay, so an analogy is to basically say at a restaurant. Okay, so this might work. Okay, I'm just creating an analogy right away. So at a restaurant, okay, we only have so many servers, right? And then we have clients, and then in the back we have the kitchen. So we definitely have resource management issues, just like with mainframe computers. So in order for the restaurant manager to prioritize, basically, which client should get their dishes done first, how should the kitchen prioritize all of those work orders, we have these classification rules. So the classification rule can look into all the work requests coming in, and it can basically ask for, in some cases, it makes sense to look for the name of the client. Okay, so if the name of the client is, okay, let's just say someone who's famous. Okay, let's say Arnold Schwarzenegger. Okay, then the classification rule can say, okay, we are going to use surface class Arnold. In other words, we basically predefine a surface class called Arnold, and then we are just using that as a identifier so that we can associate all the incoming work request, the dishes that is ordered by Arnold, to be associated with the surface class definition, the surface class called Arnold. Now, how is that surface class defined? That's a whole separate story. Okay, we are just making a link between the incoming work request and to find out what surface class we should be using for that work request. Now, but it doesn't have to be linked to the person, the name of the client. It can also be linked to the name of the dish. Okay, so let's just say that there are special dishes where they need special consideration. I'm just gonna say chocolate ice cream because that's what's in my head right now. Okay, so let's just say it's chocolate ice cream. So chocolate ice cream is not the name of the client; it is the name of the dish. So the classification rule would now specify, don't look at the name of the client, look at the name of the dish. If the name of the dish matches chocolate ice cream, then we want to link that work order to a surface class called, okay, we'll just give it the name, chocolate ice cream. Is that okay?
That's better.
But you can also use other ways to qualify a particular connection to a surface class. Okay, so we just used the name of the client. We just used the name of the food item that is being ordered. So you can think of some other stuff, right? Let's just say the number of people of that party. Okay, so if we're dealing with a large party of like 20 people, okay, so now the classification rule can say look at the number of people of the party, and then the name would specify if it is 20 or more. Okay, so now the classification rule is basically saying if a particular work order is related to a party that has 20 or more people, then the rule is matching. But what do we do when the rule is matching? So whenever a rule matches, it is always linked to a surface class. So in this case, the name of the surface class may be 20 plus. Okay, to basically, we just need to make sure that there's a name associated with the surface class. So whatever the surface class is defining in terms of performance goal, importance, and whatnot, that's a whole different story. Because what the classification rule is really trying to say is to say what should I be looking at in order to determine which surface class we should be using for this particular work request. So the high level view of a classification rule is just a mechanism to look at all the work request, all the work that is coming into the system, and link each one with a surface class. Now we talked about surface class all the way up here, and what a surface class is, even though it can have its own subcomponents called the periods, but what a surface class really is a packaging, that generally speaking, tells us about the importance of the work requested. Do we have any performance goal associated with it? Is it important? And so on. So the classification rule is just a way to make that connection between the work that is coming in and what we should be using to look at the importance and the performance goal of how that particular work request fit into the big picture.
I think I got it now.
Okay, all right.
Thank you.
You're welcome. Yeah, I know this stuff is it's not easy to understand because there are many pieces involved in all of this. All right. So now we look at what is a policy. A surface policy is a named collection of surface classes. So it's really just a name. I mean, it's just a way to relate multiple surface classes together and say these things, they work together. A surface policy can also specify changes to the surface classes that it contains. So it references surface classes as we talked about all the way up here, but it can also contain what I would call a delta, or what basically is a change. So basically you can say refer to surface class blah blah blah, but make these changes to the surface class definition. So why do we have surface policies? Because a surface policy, we can have multiple surface policies, by the way. So the system can only have one single surface definition. That's just one. Okay, the entire installation can only have one single surface definition. But under that one single definition, there can be multiple surface policies, and the system can switch between the surface policies. The policies okay, let's just consider two policies. Okay, so the two policies can refer to exactly the same surface classes. In fact, they're probably expected to refer to exactly the same surface classes. But one can refer to the surface classes and just go like, okay, we'll just use whatever the surface class is telling us and don't make any more change, don't make any changes. The other surface policy can say, look at the very same surface classes, but make changes. Now, what kind of changes are we talking about? We can change the performance goal, we can change the importance, we can change a whole lot of things. Just about anything that we defined up here when we talk about surface class, they can all be overridden when we include a surface class reference in a surface policy. So the idea of using surface policies is so that we can make adjustments. But the adjustments are based on existing surface classes. So this way you can say, during the work week, we'll just use the surface class as defined, okay, because they handle most of the cases correctly during the work week. What about the weekend? Well, over the weekend, we'll have a different policy. So the policy for the weekend can basically say, for the most part, we are going to use exactly the same surface class as defined for the work week, except for these guys. Okay, so now we can just say for these specific surface classes, we'll make some adjustments, we'll make some tweaks. Because over the weekend, let's just say that over the weekend we do not expect a lot of interactive traffic, so we can now knock down the importance level of certain surface classes because we are not expecting a lot of people to be using the website. So we're going to say, let's knock down the interactive surfaces from importance level 2, and we'll just kind of drop it down to importance level 3. But at the same time, over the weekend, maybe we'll be running a lot of longer batch jobs. Okay, because now we can run the batch job for a lot longer without impacting other kind of surfaces. So we can now say, okay, but the velocity of certain surface classes may increase because we want to allocate more resources to batch processing over the weekend. So is that okay? Does everybody understand why we have surface policies and what they are used for?
Yes.
Okay. But at any time, we can only have one surface policy in place. So you can switch between the surface policies that you might have defined under the same definition, but you can only have one being active at any particular time. All right?
Yep.
I'm just looking at the time here. So we still have a little bit more time. If we have questions about workload management, we can talk about those. If not, I can move on to talk about interrupt processing, because that's a very it's an interesting concept, and the IBM documentation has some description of it. It's not very in depth, but it has some. But first of all, I want to make sure that workload management is handled.
So hi, this is Jennifer.
Yeah, go ahead.
Number 8 and 9 are those just added, or it was there already for my note?
I cannot remember when I added these, but they were added before Monday's class, I believe.
Oh, it didn't print the 8 and 9 on my copies.
Oh,
Okay, I just need to go back and
okay. Yeah, you can actually make a copy of the original document too, and then you can add your own annotations and notes too.
Right. Okay.
All right, so I think it might be helpful to give you kind of a hierarchical view of what can contain what. Okay, so I'm gonna do a quick illustration here using a spreadsheet program. Let me see if this works or not. All right, so at the highest level, we have surface definition. The entire system only has one and only one surface definition. And if you want to change the surface definition, you're going to have to reboot the system for the new one to become effective. So that's only one of these. Under a surface definition, you can have one or more surface policies. So now we have surface policy, and I'll just use the word 1 plus to mean, at least one, but you can have more than one. For each surface policy, you have surface class. And then under each surface class, you have surface class periods. And once again, it's at least one, but you can have up to 8 in this case. So I'm going to use a range and specify you can have 1 to 8 of these. So is that kind of giving you a better idea of how these different concepts nest within each other?
Yes.
So
Yeah.
So there's no specific name for surface class periods because they are subcomponents of surface class. A surface class has a name so that the classification rule can refer to the surface classes. A surface policy also has a name so that we can refer to the surface policy that is active. The surface definition does not have a name because the entire system only has one and only one surface definition, so there's no need to use a name to identify it. But it does have to be stored in a specific and special dataset because it has to be available at startup time.
Oh, so that's my next question. We input all this information in each data set, right?
Right. So the configuration are stored in datasets, but they are stored in a special dataset, especially the system definition, which contains all of the rest,
Right.
because it has to be available when you start up the system.
Okay.
And somewhere here, I think it's in the same level, at the same level as surface policies, is the classification rules. So the classification rules are a part of the surface definition. So are we doing okay with this?
I am, yes.
Okay, very good. All right. So anytime you have any questions about topics that we have talked about in the past, you don't hesitate to ask. You can post your question in the channel text channel, because I do check those once in a while, or you can just kind of let me know in class. But sometimes you review the material and then you realize, hey, what about this? Okay, go ahead and go ahead.
Why in the material though? Did we go backwards instead of going from the top down? We went from the bottom up.
Yes, we went from bottom up. You're right.
Yeah, that makes it more difficult to comprehend, I think, for myself.
Okay.
Yeah.
Yeah, the way my mind works is, I need to drill all the way down to the lowest possible detail, and then I reconstruct the higher level concepts along the way. So so to me, I know it's different for each person. Yeah.
Yeah, but I mean, is that how you'll do things on a regular basis? Because to me, it kind of just confused me because we went from the bottom up instead of the top down. But if I know that that's the way you do it, then I could understand it, try to follow it more.
Yeah, I'm planning to do the same thing with storage devices,
Okay.
input output devices. So I was planning to go all the way down to the DASD first, and then go back up, and I would go for the DASD, the channel, and then go back up to um, the VTOC, and then from that I go back up to dataset. um, I can try to do it the other way too, using the top-down approach, but the
Well,
top.
I mean, as long as I mean, I think like if you just told me that, then it'd
Okay,
be easier for me to follow. I mean, I don't expect you to change it, but I didn't understand why we went from the bottom up versus
okay.
top down. So,
Yeah, the
okay.
reason why there's a reason behind why I use the bottom up approach, because the bottom up approach allows me to explain um, the low level detail first, and the low level detail to me are the ones that I can grasp because they are concrete. They are going like, this is a piece of hardware. It's not an abstraction. It is not something that is um, that's abstract. So I would go from concrete stuff and then go back up, so that we can talk about, so I construct bigger and bigger pieces, and then the bigger pieces, hook up with other bigger pieces to make even bigger pieces. So I suppose, this is coming from, my childhood hobby of, building stuff using Legos.
Okay.
Because when you use Legos, you basically start with the smaller pieces, and then you make larger pieces, and then you connect the larger pieces into even bigger pieces. So that's, typically how I teach not only this class. Okay, when I teach my assembly language programming class, I started off with an explanation of transistors, and then we built all the way back up to processors, and then programming of the processor. So that's just how my brain works.
Okay.
Um, but I will try to kind of warn you guys ahead of time. This is like super low. This is super duper low level stuff, but we're gonna build ourselves back up to how a normal person would look at these things. So we are basically starting from um, the deep level that an X-ray machine would show you, and then we are just backing up to a normal view of something.
Okay.
All right. I'm just looking at the time. I think I can get started with the concept of interrupts. So let me show you what I'm looking at on the side here. So I'm looking at the schedule of topics. So we are done with managing workload at this point. And the next bunch of concepts include input output request and processing, dispatching, interrupt processing, and so on. But I want to start with this one. It's just a description, so there's no notes that I have prepared for that topic just yet. But I do want to give you the idea of what is interrupt processing, because the word interrupt is a fairly common word, but it has a very special meaning when it comes to computers. But I can give you an analogy that is very easy to remember, and it makes sense. Okay, so let's just think about a very typical situation of a professor in this case, me in my office. Okay, so the professor is the processor. Okay, the processor. And typically, I have stuff to do in the office. I might be grading, I might be prepping for a class, I might be doing some other stuff. Okay, so I'm usually busy in the office doing something. But it's my office hour, so I might have students coming to visit me to ask me questions. So at this point, there's nothing related to computing, to mainframe computers, or whatever. So now the question is, how do I know that someone is trying to ask me questions during my office hour? Remember, I'm busy doing stuff, right? I'm busy typing notes, like this, or I'm busy grading, or I'm busy making questions for an exam. So now I have a student coming and go like, okay, I have some questions, okay, So what do you think is going to happen next?
You're going to stop doing what you're working on. You're going to be interrupted, and then you're going to have to go to do something else in order to answer the students' questions.
Exactly. So I have two ways to do this, okay? The first way is called polling, 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 okay? So what polling is for me to periodically look at the door or to call out and go like, okay, is anyone waiting for me? That's polling, okay? So polling requires that I have to be aware of time, and I will be the one who is going to be calling out every minute or so, just looking at the door, calling out and go like, okay, is anyone waiting for me? Does anyone have any questions? That's polling. So polling is very simple, okay? From the perspective of programming, polling is a very simple thing to do because you're now stuck in the loop, and part of the things that you have to do in the loop in all the iterations is to ask your input output devices and ask them and go like, okay, do you have anything that requires my attention? So the hard drive controller, which in the case of a mainframe computer is called a channel. So the channel may be moving a whole bunch of data around, and it's done moving stuff, and it's trying to tell the processor and go like, hey, I'm done moving this chunk of data. Do you have anything else for me to do? It can be the network card receiving a packet from the internet. The network card just says, hey, I got this packet that I just received. I don't know what to do with it. Processor, what do you want me to do with this packet? Okay. So the I/O devices in a computer are basically similar to students in this scenario. So one way is to do polling, which means the operating system would just be going around and keep asking all the devices and go like, hey, hard drive controller, do you need my attention? No? Okay, that's good. Okay, network controller, you're next. Do you have any questions for me? No? Okay, let's move on to the next item, and so on and so forth. Now, that is very simple to do, but it has one big problem. Okay, the problem is the loop has to be aware of all of the input output devices, everything that can potentially request attention from the processor. The logic of the loop has to be aware of all of these things and keep asking these questions, okay? And that complicates a lot of things because now I can't concentrate in my office anymore because every time I try to do something, I need to go like, oh, is it time for me to ask if someone is at my door? Okay, that's not a very easy way for me to continue with the flow of coming up with exam questions or grading or prepping for my classes and whatnot. So that's why polling is not a very good approach to use. So the other approach is the interrupt approach. So the interrupt approach means the processor, me, being the professor in the office, is not going to ask at all. Okay, is anyone waiting for my attention? Is anyone out in the hallway, waiting to ask me questions? I won't even bother to check. I am just concentrated with whatever task that I need to do at a time. So when a student comes and go like, okay, I need to ask TAC a question, what that person is going to do, what the student is going to do, is to knock on the door. So knocking on the door to get my attention is the interrupt. Now remember, the student is the input-output device. I'm the processor. Knocking on the door is the interrupt. So what that is going to do is that the first thing I will have to do is to kind of leave a note of, okay, I'm on question number 5 in this exam. So when I'm done answering the question from the student, this is where I need to continue my work. So the first thing I need to do is to leave a little bookmark, not unlike a TCB. Okay, it's not called a TCB, but not unlike a TCB, I leave a little bookmark on the exam questions that I'm making, so that I know where I need to go back to. And then what do? Well, then I interact with the student. The processor will now interact with the input-output device. It's like, okay, so hard drive controller, why do you need my attention? Oh, I just transferred a block of data from memory into this part of the heart of the DASD. Then I go like, okay. I got another block of data for you to transfer. Here you go. Okay. So after I'm done with interacting with the input-output device, which is equivalent to after I answer the question from the student, and the student goes like, okay, I'm good now, and I'm gonna go work on this by myself. So at that point, I'm gonna look up the bookmark that I left on my exam paper earlier so that I can go back and resume doing whatever activity I was doing before the student came in to ask me questions. Is that okay? Does everybody understand the analogy?
Yep.
Okay.
I do.
Yep. So that is what an interrupt is in the context of input-output devices, and
I have a
this is
question.
go ahead.
Do the interrupts are they only allowed to happen depending on the priority level of the type of interrupt? You know, so like if the job has a higher priority than the one that's trying to interrupt and pause it, does it stop for it to review it, or does it just keep going? It won't be interrupted by a lower priority job.
That's a very good question. But the question you asked is not about input-output devices interrupting the processor. It is about the scheduling of tasks that the processor needs to do. Now that's a whole different kind of thing. It is related to interrupts because in this case, the interrupt is coming from a timer. In other words, okay, so I know we are sort of running out of time, but you have just established a very good context. So I'm going to finish this, okay? So what you're asking is about how do we dispatch jobs? How do we dispatch tasks? When we have multiple things that we need to do at the same time, how do we prioritize and how do we handle that situation? So I have an analogy for that too. So let's just say that I'm in a lab environment. Okay, so when we have a computer lab, we typically just have students working on their stuff. Okay, typically programming in my case. So let's just say that we have a class of 20 people and they are basically working on their programs, but occasionally they need to ask me questions. Okay, and let's just say that one person has a very, very long question to ask me. So I have to be fair. I cannot just go like, okay, what you're asking me is going to take half an hour to answer, but during that half an hour, I can, the other students, cannot ask me questions anymore. So I'm going to tell that student, go like, what I can do is I can stay with you for 5 minutes, but after 5 minutes, I'm going to answer questions for another student. And if all the students have really long questions, which happens sometimes, I'm going to do this with every single student to be fair. So let's just say that we have 4 students with active questions to ask me, and each one is really long. Okay, each one is going to take me half an hour to answer. So what I would do is now I set up a timer. Okay, so I can use my Fitbit, I can use my cell phone, or I can just get one of those, dial, timer, I can get from the Dollar Tree. Okay, so I'm gonna set up a timer. Okay, I dial that thing to 5 minutes, and then I'll start answering questions and interacting with a particular student. 5 minutes later, the timer is going to go off, right? So the timer going off is creating an interrupt. That's why this whole thing relates to interrupts, because the timer is actually generating an interrupt to remind me and go like, hey, 5 minutes is up. It's time to move on to answer questions for the other student. So what I need to do at this point is I need to jot down a little bit of notes so that I can remember the context, of my question answering with the first question with the first student. That is the TCB2. Okay, so the TCB is just a bookmark, a way for me to remember where to resume when it's time to go back to resume a particular task. So after I jot down a little bit of a note and go like, okay, with student number one, we were just talking about why this program is an infinite loop. Okay, so I jot down a little note so I can remember where to get back to when I get back to student number one. So now I move on to student number two. When I switch from student number one to student number two, because of the timer going off, by the time I get to student number two, I'm going to get to the TCB corresponding to student number two, which probably has, a little reminder to myself and go like, okay, student number two has a program crashing when the input is empty. Okay, that might be what I have left behind from the last time I interact with student number two. So I'm going to pick up that TCB, okay, basically a note to self, so that I can re-establish the context when I'm continuing to answer the question for student number two. But at the same time, I'm going to turn the timer dial to 5 minutes again, because 5 minutes later, I'm going to get the timer going off to remind me, hey, it's time to move on to the next student. So I'm going to do exactly the same thing. I would write down the context of the question answering session with student number two this time. That's my TCB for student number two. And then I will move on to student number three to resume, the question answering session with student number three. And the first thing I need to do is to look at the TCB of student number three so that I can re-establish the context from the previous round of answering questions for student number three. Is that working okay?
It is for me because now it's telling me that a TCB is related to a job, and that's what it is. It's like a bookmark in order to know where it left off. So
Exactly.
But in the mainframe world, we're talking seconds on each job and then bouncing around in seconds and then going to each TCB to do something and then go on to the next one and then go back or whatever. So yeah, that helped.
And on top of
That
that,
helped me too. Thank you.
oh, sure, absolutely. And on top of that, there are two things that I want to add. It depends on the computing environment. For batch jobs, maybe going around, by the second is okay. But when you're talking about Linux and talking about Windows, things that are on a personal computer, the task switching, happens in at the most, tens of milliseconds. In other words, we are switching between things to do. The processor is switching between the processes every 25 milliseconds, 50 milliseconds. So what that translates to is it would do this like 20 times per second. So this way, it doesn't look like, one window stays kind of stuck for a minute, for a second, and then it moves a little bit again. And everything is moving kind of in a fluid way because we cannot tell the difference when the processor is switching between the tasks, like 50 times per second. We cannot tell the difference anymore. So that's the first point. The second point is when I'm doing this, answering questions for multiple people, I can throw in prioritization. So that means, certain jobs are more important. So if one particular student has okay, this doesn't happen in my class, because I have to be fair, but I'm just using this as an example, okay? So let's just say that I have one particular student who has special needs, okay? And that student now has a higher importance level. So what that means is I am not going to help other students until this student is completely helped. All right, so this is where what we are just talking about, basically we are talking about dispatching to different tasks tie in with workload management. Because now we can use the performance goals that we have just talked about and apply that to how I allocate my time to answer questions for different students, because now I can say, well, for these students, the performance goal is this. And then for these students, the performance goal is that. And then the importance level is this, the importance level is that. And so that way, I can now, I do not necessarily have to allocate my resources evenly between all the students. I can now say, okay, I'm going to spend more time with these students, or I cannot help those students until I'm done helping these students. So that's how the WLM comes in when it comes to, okay, we got all of these things to do, but how do I allocate my resources? It's the WLM combined with the performance goals that will help determine, how I allocate my time. So I'm hoping this helps to kind of tie everything in together a little bit.
I think it did. Thank you.
All right, you're welcome.
Yes, it did. Thank
All right, well, we are out of time today, and today is Wednesday. So we got 5 days. So if you guys go back in to review this stuff and you have any questions, just let me know, and I'll try to find the answers for those things while at the same time preparing for the next lecture on Monday. So have a
Okay.
nice weekend.
Thank you. You too.
All right, thank you.
Thank you.
Yes, you have a nice weekend.
All right,
Good
thank
night.
you.
Bye.
Okay, bye.